Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Digital Signal Processing Part 1 from the paper Electronics. So students, let us see what we are going to learn in this module. First, we will discuss the block diagram of digital signal processing along with sampling, quantization and coding. Secondly, we will discuss about the sampling of analog signals. Third, the aliasing phenomena along with an example will be illustrated. Next, we will discuss about the sampling theorem along with the description of sampling in time domain and in frequency domain. So students, let us start with a basic introduction about the module. Digital signal processing provides inexpensive and relatively fast digital circuits to construct highly sophisticated digital systems capable of performing complex digital signal processing and tasks which are very difficult and expensive to be performed by analog signal processing systems. This figure shows the block diagram of digital signal processing system. So students, as you can see from this figure, there are the basic component of this system is the analog to digital converter. Analog to digital conversion is a three-step process which is described as number 1, sampling. This is the conversion of a continuous time signal into a discrete time signal obtained by taking samples of the continuous time signal at discrete time instants. So if XAT is the input to the sampler, the output is XA as a function of NT, which is equal to Xn, where T is the sampling interval. Next process is quantization. This is the conversion of discrete time continuous valued signal into a discrete time discrete valued digital signal. The value of each signal sample is represented by a value selected from a finite set of possible values. So the difference between the unquantized sample Xn and the quantized output Xqn is called the quantization error. The last process is coding. In the coding process, each discrete value Xqn is represented by a b-bit binary sequence. So students, the block diagram for the analog to digital converter is shown in this figure, where all the three steps, that is sampler, quantizer and a coder, which performs all these processes, are shown over here. Sampling of analog signals. The periodic or uniform sampling is most often used in practice, which is described by the relation Xn equal to Xant, where n is varying from minus infinity to infinity, where Xn is the discrete time signal obtained by taking samples of the analog signal Xat after every t seconds. So this process is clearly shown in this figure, where on the left hand side the continuous XAT signal is shown, and on the right hand side the sampling of this continuous signal is shown over here. The time interval T between successive samples is called as the sampling period or sampling interval, and 1 by T, which is equal to Fs, that is the sampling rate or sampling frequency. This is related with the time period as T equal to N, T equal to N by Fs. As a consequence of this equation, there exists a relationship between the frequency variable f for analog signals and the frequency variable small f for discrete time signals. So let us now discuss the mathematical analysis of this process. Consider an analog sinusoidal signal of the form xat equal to a cos of 2 pi ft plus theta, which when sampled periodically at a rate fs equal to 1 by t samples per second, it yields xant equivalent to xn is equal to a cos 2 pi fnt plus theta, where we replaced small t by n multiplied by capital T. This is equal to a cos 2 pi nf by fs plus theta. Now here we have put t equal to 1 by fs. So comparing it with discrete time signal xn equal to a cos 2 pi nf, that is small f, plus theta, where n is varying from minus infinity to infinity, and f, which is for the discrete signal, equal to capital F by capital Fs of continuous time signal, or equivalently this W is equal to omega multiplied by t. Now for continuous time sinusoids, the f, capital F, basically is varying from minus infinity to infinity, and omega is varying also from minus infinity to infinity. However, for discrete time sinusoids, the fundamental range is omega varying from minus pi to plus pi, and the small f is varying from minus half to plus half. So by putting equation 5 and 6 into equation 8, the frequency of continuous time sinusoid when sampled at a rate of fs equal to 1 by t must fall in the range minus 1 by 2t equal to minus fs by 2 less than equal to f less than equal to fs by 2 equal to 1 by 2t, or minus pi by t equal to minus pi fs less than equal to 0 less than equal to pi fs. Here less than equal to omega less than equal to pi fs, this is equal to pi by plus pi by t. Since highest frequency in a discrete time signal is omega equal to pi or f equal to 1 by 2, the corresponding highest value of f and omega are f max is minus fs by 2 equal to 1 by 2t and omega max equal to pi fs equal to pi by t. aliasing. So let us now discuss the process aliasing. The sampling of a continuous time sinusoidal signal, that is XAT, equal to A cos 2 pi f naught, capital F naught, plus theta. So with a sampling rate Fs equal to 1 by t, it results in a discrete time signal Xn equal to A cos 2 pi f naught n plus theta, where small f naught is equal to capital F naught by capital Fs. If we assume capital F naught varying from minus Fs by 2 to plus Fs by 2, the small f naught of Xn is in the range of minus half to plus half, which is the range of discrete time signals. So here, the relation between capital F naught and small f naught is 1 to 1. This implies that it is possible to identify or reconstruct the analog signal XAT from Xn. On the other hand, if the sinusoids XAT equal to A cos 2 pi fkt plus theta, where Fk is equal to F naught plus Kfs. Now here K is varying from plus minus 1, plus minus 2 and so on. They are sampled at a rate of Fs. It is clear that the frequency Fk is outside the fundamental frequency range. That is, F naught is varying from minus Fs by 2 to plus Fs by 2. So the sampled signal is represented by Xn equal to Xant is equal to A cos of 2 pi f naught plus kfs by fs n plus theta, where t is replaced by nt equal to n by fs. So this is equal to A cos 2 pi f naught by fs plus theta plus 2 pi kn, which is equal to A cos 2 pi f naught n plus theta. Now here capital F naught by capital Fs is replaced by small f naught, which is identical to the discrete time signal in equation 4 obtained by sampling equation 3. Thus, an infinite number of continuous time sinusoids is represented by sampling the same discrete time signal. Consequently, if we are given the sequence Xn, an ambiguity exists as to which the continuous time signal Xat these values represent. So equivalently, we can say that the frequencies Fk equal to F naught plus Kfs, where k is varying from minus infinity to plus infinity, indistinguishable from the frequency capital F naught after sampling, and hence they are aliases of F naught. So let us now discuss it in detail by considering an example. So consider two sinusoids with frequencies f0 equal to 1 by 8 and f1 equal to minus 7 by 8, and they yield identical samples when sampled at a rate of fs equal to 1 Hz. So for k equal to minus 1, f1 equal to f0 plus kfs, which is equal to minus 7 by 8 for k equal to minus 1. This is diagrammatically shown in this figure. Now since fs by 2, which corresponds to omega equal to pi, is the highest frequency that can be represented uniquely with a sampling rate fs. So it is a simple matter to determine the mapping of any alias frequency above fs by 2 omega equal to pi into the equivalent frequency below fs by 2. So we can use fs by 2 or omega equal to pi as the pivotal point and reflect or fold the alias frequency to the range omega varying from 0 to pi. So since the point of reflection is fs by 2 omega equal to pi, the frequency fs by 2 omega equal to pi is the folding frequency. Let us now discuss about the sampling theorem. To avoid the ambiguities resulting from aliasing, we must select the sampling rate to be sufficiently high. That is, we must select fs by 2 to be greater than fmax. So, in order to avoid the problem of aliasing, fs should be greater than twice of fmax, where fmax is the largest frequency component in the analog signal. So here, if the highest frequency contained in the analog signal xat is fmax equal to b and the signal is sampled at a rate fs greater than twice fmax equivalent to 2b, then xat can be exactly recovered from its sample values using the interpolation function, that is gt equal to sine of 2 pi bt divided by 2 pi bt. So thus xat may be expressed as by the reconstruction formula, that is xat is equal to summation from n equal to minus infinity to infinity over xa as a function of n by fs multiplied by g as a function of t minus n by fs. When the sampling of xat is performed at the minimum sampling rate fs equal to 2b, the reconstruction formula becomes xat equal to summation n equal to minus infinity to infinity over xa n by 2b multiplied by sine of 2 pi b t minus n by 2b divided by 2 pi b t minus n by 2b. So the sampling rate fn equal to 2b equal to 2f max, which is called as the Nyquist rate. So let us now study the sampling process in time domain. Xn equal to xant, where n varying from minus infinity to infinity. So sampling analog signal xat periodically every t second to produce a discrete time signal xn. The sampling frequency fs must be large enough. This implies that sampling does not cause any loss of spectral information, that is, there is no aliasing. So if the spectrum of xat is recovered from the spectrum of xan, there is no loss of information. Sampling in frequency domain. The voltage spectrum of the periodic signal xat is given by Fourier transform relation. xaf equal to integral minus infinity to infinity over xat exponential minus j2 pi ft dt. So utilization of all frequency components f varying from -infinity to infinity is a must to recover xat if xat is not band limited, and xat equal to integral -infinity to infinity over xaf exponential j2 pi ft df. Similarly, the spectrum of a discrete time signal xn, which is obtained by sampling xat, is x omega equal to summation n equal to -infinity to infinity over xn exponential minus j omega n, or xf equal to summation n equal to -infinity to infinity over xn exponential minus j2 pi fn. So the sequence xn can be recovered from its spectrum x omega or xf by the inverse Fourier transform, that is xn equal to 1 by 2 pi multiplied by integral minus pi to pi over x omega exponential minus j omega n d omega. This is equal to minus half to half xf exponential j2 pi fn df, where omega is varying from minus pi to pi and f is varying from minus half to half. So periodic sampling imposes a relationship between the independent variables t and n in the signals xat and xn respectively. That is, t small t equal to n multiplied by capital T equal to n by fs. So this relationship in the time domain implies a corresponding relationship between the frequency variables capital F and F in xaf and xf respectively. So substituting this equation 4 in equation 1a, we get xn equal to xant equal to integral -infinity to infinity xaf multiplied by exponential j2 pi nf by fs df. So comparing this with equation 3, we get xn equal to integral minus half to half xf exponential j pi 2 pi fn df equal to integral -infinity to infinity capital XAF multiplied by exponential j2 pi nf by fs df. We already know that f equal to f by fs, that is small f. So your df small f will be equal to d capital F by fs. And if f is plus half, which implies f is fs by half. So thus equation 5 will become 1 by fs integral minus fs by 2 to plus fs by 2 xf exponential j2 pi f by fs df is equal to integral -infinity to infinity xaf exponential j2 pi nf by fs df. So the integral range -infinity to plus infinity of the RHS can be divided into an infinite number of intervals of width fs, that is the sample frequency. Thus, the integral over the infinite range can be expressed as the sum of the integrals, that is integral -infinity to plus infinity xaf exponential j2 pi f by fs df will be equal to summation k equal to minus half to plus half integral k minus half fs k plus half fs, the limits of integration, and over xaf exponential j2 pi nf by fs df. So here xaf in the frequency interval k minus half fs to k plus half fs is identical to xa f minus kfs in the interval minus fs by 2 to plus fs by 2. Consequently, the summation over k plus k minus half fs to k plus half fs integral xaf exponential j2 pi nf by fs df equal to summation k varying from minus infinity to infinity minus fs by 2 to plus fs by 2 integral over xaf minus kfs exponential j2 pi nf by fs df. So, where we have used the periodicity of the complex exponential, namely exponential j2 pi n f plus kfs by fs exponential j2 pi n f by fs. So, comparing equation 6, 7 and 8, we conclude that xf equal to fs multiplied by summation k equal to minus infinity to infinity xaf minus kfs. Now here xf is the spectra of discrete time signal, xaf is the spectrum of analog signal, or equivalently x as a function of small f equal to fs summation over k equal to minus infinity to infinity over xa f minus k multiplied by fs. Now where small f is f by fs and capital F is small f multiplied by fs. So periodic repetition of the scaled spectrum fs xaf with periodicity fs, that is, the period of xf is fp equal to 1 and fp equal to fs. So let us now study this by considering an example. Suppose that the spectrum of band-limited analog signal is shown below. The spectrum is 0 for modulus f greater than equal to b. Now, if the sampling frequency fs is selected to be greater than 2b, then the spectrum xf of the discrete time signal is shown in this figure. So here, if the sampling frequency fs is selected such that fs is greater than equal to 2b, where 2b is the Nyquist rate, then xf equal to fs xaf, where capital F the modulus is less than equal to fs by 2. So in this case, there is no aliasing, and therefore the spectrum of the discrete time signal is identical to the spectrum of the analog signal within the fundamental frequency range, that is modulus of f is less than equal to fs by 2 or modulus of small f is less than equal to half. Now on the other hand, if the sampling frequency fs is selected such that fs is less than 2b, so the periodic continuation of xaf results in the spectral overlap, which is shown in this figure. Thus, the spectrum xf of the discrete time signal contains the aliased frequency components of the analog signal spectrum xaf. End result is that the aliasing which occurs prevents from recovering of the original signal xat from the samples. So given the discrete time signal xn with the spectrum xf as shown in the above figure with no aliasing, it is now possible to reconstruct the original analog signal from the samples xn in the absence of aliasing. That is xaf equal to 1 by fs xf, where modulus of capital F is less than fs by 2, and it is equal to 0 where modulus of f is greater than fs by 2. So by the Fourier transform, we have xf equal to summation from n equal to minus infinity to infinity xn exponential minus j2 pi nf by fs. Now where small f is f by fs. So the inverse Fourier transform of xaf is xat equal to integral minus fs by 2 to plus fs by 2 over xaf exponential j2 pi ft df. Now here modulus of f is less than equal to fs by 2. So let us assume that fs is greater than equal to 2b. So with the substitution of above equations 10 and 11 in equation 12, we get xat equal to 1 by fs integral minus fs by 2 to plus fs by 2 over summation of n equal to minus infinity to infinity xn exponential minus j2 pi fn by fs multiplied by exponential j2 pi ft df. So now simplifying, we get at the final, that is summation n equal to minus infinity to infinity xant multiplied by sine of pi by t multiplied by t minus nt divided by pi by t multiplied by t minus nt, where xn is equal to xant and t equal to 1 by fs. So this is the reconstruction formula, appropriately shifted by nt equal to, where n is equal to 0, plus minus 1, plus minus 2 and so on, and multiplied or weighted by the corresponding samples xant of the signal. So the reconstruction of xat from its samples using above formula is called as the ideal interpolation formula. So students, let us summarize what we have learned in this module. Firstly, we discussed about the block diagram of digital signal processing along with three important phenomena, that is sampling, quantization and coding. Secondly, the sampling of analog signals was discussed in detail. Thirdly, the illustration of aliasing along with an example was done in this module. Lastly, a very important theorem in communication system, that is sampling theorem, along with the description of sampling in time and frequency domain was discussed in detail. Thank you.